Let's start with this practice problem here. You have a diver and she springs upward from a board that's 3 meters above the water. At the instant she contacts the water, her speed is 9 meters per second. If she had a magic speedometer in the belly, it would read 9 right as her fingers touch the water. And she enters the water going at an angle of 75 degrees with respect to the surface of the water. We're asked to find the initial velocity vector. Now, a velocity vector, or any vector, has two parts. The magnitude, always a positive number, that's the size. That's represented by the length of the vector. And then the direction. Okay? Now, let's do this problem together. There's the board. It's 3 meters above the water. I don't know why the water's yellow. Maybe not enough chlorine. She dives in a parabolic arc, and when she enters the water, her body is moving 75 degrees with respect to the horizontal surface of the water. Now, from the moment that her toes leave the board to right before her fingers touch the water, she's in free fall. Her acceleration is 9.8, call it 10 meters per second every second, down. Now, folks, what I'm seeing is a lot of people are trying to solve these projectile motion problems without the table. If you don't have that table, you're likely to get the problem wrong. That's been my experience over the years. Okay? So do yourself a favor. Whenever you see that something's going in a projectile motion, immediately make that table. Now, in the coordinate system that we typically choose, where up is positive y, the y part of the acceleration is negative 9.8, call it negative 10 meters per second every second. And there's no acceleration in the x direction. Now, she ends up 3 meters below where she starts out. So that's a minus 3 meters. Okay? The delta y. My question is, where do I put that 9 meters per second? Nowhere. Absolutely nowhere. Folks, what I find over and over again is that people use these equations incorrectly. These are one-dimensional equations. You can either use them for the x list or you can use them for the y list, but you can't mix and match. And that 9 meters per second is not in the x direction, it's not in the y direction. I can't put it in any of those equations. Okay? And so I have to break that vector up into its x part and its y part. Now, the x part is going to be the 9 times cosine of 75 degrees, because that x part is cozy with the angle. And the y part is going to be the 9 times the sine of 75 degrees. Now, that vector goes to the right and down. It's to the right, so it's positive x. It's down, so it's negative y. Now, when I use my calculator, I get 2.3 and negative 8.7. Now, here's half the problem. Remember what we're trying to do here. We're trying to find the initial velocity vector at which she launches off the board. That's our goal. Well, that velocity vector has an x part and it has a y part. I just found the x part. Because the acceleration in the x direction is 0, the initial and final in the x direction is always the same. It's like taking this and every second adding 0 to it. And so that means I've got half my problem done. I know that the x part of the initial velocity is 2.3 meters per second. Now, if I find this y part of the initial velocity, I'm done. So what I'm looking for is this right here. That makes the time, who cares? And that means I go to the equation that doesn't have time in it. There's time, there's time, there's time. I have to use that last equation. And I just plug and chug at this point. The 8.7 goes here. Notice I didn't waste any ink or any blue photons there, because I'm going to square it anyway. I have this that I'm looking for. I've got my acceleration here. I've got my negative 3 here. Both of these minus signs are critical. If you leave out one of those, you're going to get a drastically wrong answer. If you leave out both of them, you get the right answer, but you shouldn't. That's just a fluke, okay? 2 rights don't make a wrong, but 3 lefts make a right, okay? Okay, now, I get V initial squared is equal to 16. That gives me the answer of V initial y is equal to plus 4 or minus 4. I choose the plus 4 because she's going up. Now, the speed, if she had a speedometer in her belly, the speed is the magnitude of this total velocity vector. And that's going to be, by Pythagorean theorem, 2.3 squared plus 4 squared square root. And if I had asked her at what angle she left the board, well, that would be given by the inverse tangent of the opposite side over the adjacent side. Remember, there's only 2 trig problems that we solve in this class. Over and over and over. And that's the second one. And we talked about that the second day of class. Okay, see if your neighbor's on board with this problem. Yes, sir.
On the exam, do you care if we include units in our work?
Oh, as long as the units are in your final answer, we'll be fine with it. Okay, often I leave out the units as I work through and then put it in at the end. And I don't do that because I'm lazy. I'm not saying I'm not lazy, I am lazy, but I'm finding that if I put in all the units all the way through, sometimes people get lost in the mess. And if I just put the numbers, they can see it better. So it's not that I'm sloppy. I found that this works. Okay. This problem, problem 13. It turns out that, I know this will surprise you, but I was a terrible athlete. I could not, for the life of me, play sports. And so I just assumed that my children would be terrible as well. My youngest in junior high kept on bugging me to go to his basketball game. I'm busy. So finally he says, "Hey, Dad, I'm in the championship game. You gotta come." So I made arrangements. I went to the game, and lo and behold, he's the star. He makes every single basket for his team, and they win. Now the kid who's making all the baskets for the other team, his name is Mo Sparks. I kid you not. And it turns out that my son Matt and Mo Sparks actually lit a field on fire with fireworks. The fire truck had to come. It's kind of comical. Mo Sparks, think about it. Anyway, that prompted me to write this problem here. Matt shoots at 20 meters per second at an angle of 53 degrees above the horizontal. 3 seconds later, the ball swooshes through the hoop. His friend Mo is waiting directly under the basket. The questions that follow, you can neglect air resistance and assume G is 10. You'll always be able to make those assumptions. We're looking for how far Matt is from Mo when Mo's under the basket. That's my delta x. What's the y component of the ball's velocity when it goes through the hoop? That's v final y. What's the speed of the ball when it goes through the hoop? That's the magnitude of the total velocity vector. Okay, that's v final x squared plus v final y squared square root. Now, how much higher is the hoop than the release point of the ball? That's delta y. Now these problems, just like one-dimensional problems, can be worked two ways. Either with your gut and the operational definitions, or just by blindly plugging into the equations. I'm going to do it first with my gut, and then I'm going to go back and do it with the equations. Okay. Right at noon, Matt fires the basketball at 20 meters per second, and because nature treats the x part of that different than the y part, we have to treat it differently. So I break that up into its x part and its y part. Now again, this is 53 degrees, this is a 3, 4, 5 triangle, and so that means I've got 16 and 12. That's 3 times 4, 4 times 4, 5 times 4. Now, as we watch that ball fly through the air, at t equals noon plus 1 second, well, the x part of the velocity is still 12 meters per second. That does not change. What does change is the y part. Nature takes what you handed in the y direction and adds 10 meters per second down. So that means if I start with 16 up and I add 10 down, I've got 6 up. Now, if this ball had a speedometer, that speedometer would read that velocity right at that time, and that would be equal to 12 squared plus 6 squared square root. And if I asked you for that angle would be the inverse tangent of the opposite side over the adjacent side. Now, let's wait another second. T equals noon plus 2 seconds. The x part of this ball's velocity would still be 12 meters per second. But the the y velocity, you had 6 up, nature adds 10 down, that gives you 4 down. And the actual speed of this thing would be 12 squared plus 4 squared square root, and you could find that angle. Now, at t equals noon plus 3 seconds, it goes through the hoop. Now, as it goes through the hoop, the x part of the velocity is still 12, that never changes. But now the y part, I had 4 down, I had 10 down, that gives me 14 down. And the speed, as it goes through the hoop, is going to be 12 squared plus 14 squared square root. Okay. Now let's answer those questions. In the x direction, every second that goes by, the ball goes 12 meters to the right for 3 seconds. How far did it go to the right? 36 meters. Easy peasy. The speed, the y component of the ball's velocity is going to be 14 meters per second down, or I could also say that is negative 14 meters per second. Now, the speed is going to be the 12 squared plus the 14 squared square root. The last one, we need to use a little bit of common sense. How much higher is the hoop than the release point of the ball? Well, that's delta y. And that's going to be the average velocity in the y direction times the time of flight. Well, I start out with 16 up and I end up with 14 down. What's the average? What's halfway between 16 up and 14 down? And the answer is 1. How did I get that? Well, that V average, spelled with an E, in the y direction is going to be the plus 16 plus the minus 14 over 2. And that's going to give me plus 1 meter per second.
Wasn't it plus 6 meters per second for your initial velocity in the water?
I can't hear.
Wasn't it positive 6 meters per second for your initial velocity in the water?
Your initial velocity when you fire is 60. Yep. So, on average, this ball is going up 1 meter each second for 3 seconds. Okay? So that means that the hoop is 3 meters above where Matt released it. Now, a basketball hoop's just a little bit over 3 meters, so that means Matt's pretty short. And Matt objected to that in this problem, but Matt is pretty short, and that's why I didn't believe he was a basketball star. So, okay, now, let's solve this without our brain, okay? That's how you do it with your gut. Let's just plug and chug. Okay, once it leaves Matt's fingers, it's in free fall. Okay, 9.8, call it 10 meters per second down. I can't solve these problems without the table. And I put things in that table relative to this coordinate system. In that coordinate system, the acceleration is negative 10 on the y side and 0 on the x side. That 20 meters per second cannot go into any one of these variables. It's not x and it's not y. I've got to bust it apart because nature busted it apart. And so I have 12 and 16, like we broke it up over there. Now, we're told that the time is 3 seconds, so I can put that in both lists. Now, because this acceleration in the x direction is 0, the 12 meters per second that I start with in the x direction stays 12 meters per second. So now, I've got 1, 2, 3 things in this column. I can solve for the other 2. I've got 1, 2, 3, 4 in this column. I can solve for that one just by plugging into those equations up there. Let's look for v final y first. I just say, I started with 16 up. Every second that went by, I added 10 down. And that's what gave me my minus 14. If I look for delta y, I can use any one of those equations that have delta y in it. Would give you the same answer. I tend to use the first 2 equations whenever I can because they're the fundamental equations. So in this case, I would have 16 up plus 14 down. The average would be 1 up times 3, which would give me 3 meters. Now, that's easy. But I'll issue this warning. When this was on an exam, many people missed it, and this is why they missed it. They said, that ball is flying through the air for 3 seconds. That's 1.5 seconds up and 1.5 seconds down. Why is that not only wrong, but sick and wrong? Talk to your neighbor. Why is that sick and wrong? Okay. A ball will spend just as much time going up as it comes down if it starts and ends at the same height. But in this case, the ball ended higher than it started by 3 meters. And so it had to spend more time going up than it did coming down. Now it's this y part of the velocity that tells me how long it's going to be going up. Can you tell by looking at that how many seconds it's going to be going up? Let me see if I can help. If I throw a ball straight up with 30 meters per second, straight up, how many seconds till it stops at the top? 3. Because every second that goes by, I've got to subtract off 10. What if I throw it at 20 meters per second? How many seconds to stop? 2. What if I throw it at 25 meters per second? 25 meters per second? 2.5. Okay. Well, if I throw it up at 16 meters per second, it takes 1.6 seconds to go up. Okay? And if I wanted to know how high it goes at its highest point, that would be the V average up times the delta T up. Well, going up, it starts with 16 and it ends with 0. That's going to be an average of 8 meters per second up with a time of 1.6 seconds. And that's going to give me 12.8 meters. That's how much higher than the release point it will be at the highest point. So this ball spends 1.6 seconds going up and 1.4 seconds going down. Okay, check that your neighbor is following all of this. Are there questions? Let's get it figured out. Okay, before we go and lose all our time, I want to make sure that you know how to do these problems where you're asked to find the direction of the velocity and the direction of the acceleration for two-dimensional motion. I have this problem called the March of the Penguins. In this problem, the penguin starts from rest at A, waddles just as fast as he can speed up until right here at the end of the platform, hits his belly here, we ignore friction, and we're asked to find the velocity and acceleration vectors at each of those points. Now I've placed a solution to this at the D2L site if you want to go back and review. So the velocity vectors are pretty easy. They're always tangent to the curve. They're always in the direction you're going. If the penguin starts from rest, then by definition the velocity is 0 at A. At B, he's going to the right. Now, he speeds up, 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 cruise control. Okay? So that means the speed at C has to be greater than at B. It's got to be a longer vector. When you go downhill, you speed up, so the vectors get longer. When you go uphill, they get shorter, you slow down. And at H, the penguin turns around and goes back down. So in order to turn around, you've got to stop. Now let's put the acceleration vectors on. When you're looking for acceleration vectors, remember that there are 3 flavors of acceleration: speeding up, slowing down, and turning. And you can mix some of those flavors. So you ask yourself at each point, which flavors do I have? Well, at A, you're starting from rest. You're speeding up. You can't slow down from rest, and you can't change a direction that you don't have. So that means you have to just speed up. So the acceleration vector would be in the direction of the next velocity a short time later. It would also be tangent to the path. At B, the penguin is speeding up in a straight line. That means the acceleration would be in the same direction as the velocity. At C, the penguin is not speeding up, the penguin is not slowing down, the penguin is not turning, the path is straight, and so that means that the acceleration is 0. At D, the penguin is speeding up and turning right. And that means I need an angle between acceleration and velocity less than 90 and towards the inside of the curvature. You can see that this vector is partially along, that would be the speeding up, and partially perpendicular, that would be the turning right. Okay? At E, we're also speeding up and turning, but this time we're turning to the left. So the vector would be less than 90 degrees, but towards the inside of the curvature. At F, you are not speeding up and you are not slowing down. You were speeding up, you will be slowing down, but F is the point where you take the foot off the gas pedal and reach for the brake. And so at that point, you're only turning, and so you would have an acceleration vector 90 degrees with the velocity. At G, you are slowing down and turning left, so my angle would be greater than 90 degrees and towards the inside of the curvature. At H, I'm coming in before I go the other way. And so just like our bungee cord problem, the acceleration would be back along the path. Check that your neighbor could do one of these problems, because you will have to do one of these problems tomorrow. Okie dokie, questions on that? Yes, sir.
There's a question on the homework that asks which of the curves would have higher acceleration? Is it the tighter curve?
Right. In this problem, and you'll see it when you look at the actual problem statement on the D2L side, it only asks for the direction of the acceleration, not the magnitude. The velocity vectors were supposed to be drawn to scale, but the acceleration vector is just the direction. And unless you're going at cruise control at 30 miles an hour around the whole path, you really can't compare yet. In a couple of weeks you will be able to, but right now we can't compare which turn is going to have the biggest acceleration if they're not going the same speed at those two turns. Okay? Good question. Thank you for asking it. Let's look at this problem, which doesn't look like what you had in your book. Originally, it was written this way, and it was Steve Iger that was being chased by the bear. And the problem with this question was that, well, everyone knew that Steve Iger was going to have to die in every exam. And so when we asked the question, does he make it? Some people on the exam just said, well, no, it's Steve Iger. They didn't do any math, any calculations. They said, of course not. Why would he? So anyway, when Ron Hellings rewrote the book for the national audience, he said, well, no one outside of Bozeman is going to know who Steve Iger is, so we'll change it to a Cub Scout. Ron didn't know that the guy doesn't make it. And so with the Cub Scout not making it, that just makes it a mean problem. Who's going to want to buy that book? And we're going to have to change this before it goes to print. Okay. Now, Steve leaps with a mighty leap. He leaves the bare side of the canyon at a velocity of 10 meters per second with an angle of 53 degrees. So he leaves at 10 meters per second, and that is 53 degrees, 53 with a 3. Now, we're first asked to break up that velocity vector into its x part and its y part. The x part would be to the left, and the y part would be up. And if I recognize this as a, that's gone forever. Yep, okay. That color is no longer available to us. If I recognize this as a 3, 4, 5 triangle, this is 5 times 2, so this is going to be 3 times 2. And this will be 4 times 2. Okay? And then the next part of the question is just, does he make it? Now, this is a projectile motion problem. And so we start with our list. From the moment that Steve leaves his side of the canyon, he's in free fall. And so we have acceleration 9.8, call it 10 meters per second down. in our coordinate system, and since he's running to the left, I've chosen to the left as my positive x direction, just to get rid of some minus signs. In that coordinate system, the acceleration is still minus 10 in the y and 0 in the x. I break up that initial velocity into its components, and I put them into the table where they belong. Now, because of this 0 here, I can also put 6 meters per second there. And now we're stuck. It looks like we have enough information because I told you, I promised you, if you had 1, 2, 3 pieces of information, you were golden. You could solve for the other 2. And so if you use those 3 pieces of information to solve for time, you could put the time here, and then you could solve for the empty spaces over in this list. However, I might have lied to you. Not so much a lie, but I told you almost the truth. Usually, with one exception, knowing 3 pieces of information in a list is enough to find the others. This is the only exception. When this is 0, these have to be the same value. They're not independent of each other. So if I try to use these 3 pieces of information to find the time, well, I'd do that like this. V final x is equal to V initial x plus AX delta t. What that tells me is that 6 meters per second is equal to 6 meters per second plus 0. Because that's 0, I don't get to solve for delta t. And it didn't give me very interesting information. I knew that 6 was 6. I've known that for a while. Okay? Likewise, if I try to solve for delta x, I would use this equation. And you see the problem immediately. Because this is 0, I lose all information about delta x, and I get 36 is equal to 36. Also a true statement. So, here's how you solve these problems. What you do is you set up a wall of saran wrap. Go down to Costco and get one of those great big Mondo boxes of saran wrap and build a great big wall. Okay? And so if this is the cliff, you want to build a wall that just runs right along the rock and up. And that wall is built very simply by forcing delta x to be 18 meters. Okay? By forcing delta x to be 18 meters, you're saying that this person, whether it be a Cub Scout or Steve Iger, has already traveled 18 meters to the left and is somewhere at this wall. And what we want to know is, where is he in the y direction? I mean, if he punches through that wall right here, if his delta y is that, he's going to make it. If he punches through there, he's going to make it. If he punches through there, he's going to barely make it. Now remember, that's my 0, 0 right there. That's my starting point. And this was 12 meters down. So that means if I get a delta y of negative 12, he'll just barely make it. Well, let's see what we get, shall we? First off, if every second that goes by, this person goes 6 meters to the left, how many seconds is it going to take to get to the wall? 3 seconds. So I put 3 seconds in there. Now I have 1, 2, 3 pieces of information. I'm looking for delta y. That makes V final my who cares. I plug in my values. There's my V initial y. There's my acceleration in the y direction. there's my time, and what I get is negative 21 meters, which means that Steve Eiger ends up there, 9 meters below the lip, because he's Steve Eiger. Now, in my defense, shortly before we wrote this problem, every cell of my body was turned to ooze by some sort of a process that happened in his physiology class. Okay, so it was fair. Questions on this problem?
Did you set it up where you just set delta y equal to negative 12?
Yes.
You know where you is at negative 12?
Yes, you could set up a horizontal barrier that he passes through. The problem is you'll have to solve a quadratic equation, because in the y direction, your acceleration's not 0. And so when I get to, when I'm solving for my time, I'll have to use this equation without a 0 there, and it becomes messy. It's always simplest mathematically to set up your vertical wall. You could do it both ways if you really like the math.
You can solve for Z final that way without using and then use that V final to not.
Well, I can't find the V. Oh, I see what you're saying.
Yeah.
You're saying you set this delta y, solve for V final, and then use a different equation to find time. You could. That'd be a 3-step way. Yep. My way is a 1-step way. Okay. No, they both get the right answer. And you get full credit if you did it that way, and probably bonus points for being creative. Okay? Okay, let's look at this problem with Rolf Wilson. Rolf is an athlete here in town. He's given us permission to use his name in the book. What happens in this problem is that Rolf goes off this jump, and he comes down with some final velocity. And we want to design this jump so that his final velocity is in the same direction that the hill is going. So in other words, if he comes down with a final velocity like that, we would like the hill to look like that. And we want to know what angle we should make that hill. Now, if I look at that final velocity vector, it has a y part that is down and an x part that's to the left. And so what we're looking for is this angle here. And you can see that that angle is given by the inverse tangent of the opposite side over the adjacent side. So if I just do these two things here, I'd be done. Well, let's do this problem together. As soon as he leaves the jump, he's in free fall. We need our list, our table. Again, he's moving to the left, so I'm going to call the left positive x direction. The acceleration I put in first, it's negative 10 on the y and 0 on the x. Now, I know that he ends up 30 meters lower than he starts. I'm not saying he travels 30 meters. He travels much further than 30 meters. But in the y direction, he travels down 30 meters. So that would be a negative 30 meters. Now, his initial velocity is 10 meters per second. But I can't put 10 into any of those spaces there because it's not in the x direction and not in the y direction. That 10 is at an angle of 16 degrees. Now, I wanted to make it 37, but Rolf said, no, that's not what I did. And so we made it 16 to make him happy. Anyway, the x part is going to be equal to 10 meters per second times the cosine of 16 degrees, and that's 9.6 meters per second. The y part of that is going to be 10 meters per second times the sine of 16 degrees, and that's going to be 2.8 meters per second. So I put those in the table. Now, because of this 0, I know that this 9.6 is always 9.6. So I put it in again. Now that means I'm halfway done. I know that this is 9.6, and so that means in my answer, I can put 9.6. So all I really need right now is the final y velocity. Well, I have 3 pieces of information in the y list. That makes my time, who cares? I solve the equation that doesn't have time in it. I just plug and chug. I get this value. When I take the square root, I have 2 answers, either a positive or a negative 24.6. He's going down and to the left. The down means negative y. So I choose the negative 24.6. Now when I go over here, I just label that as 24.6. I don't put the minus sign in because I'm labeling a vector that already gives me the direction. And when I put it into this trig function, I don't put the minus sign either. The trig function, sine, cosine, and tangent, are ratios of the length of different parts of the triangle. Lengths have to be positive. You've never had a table that was negative 5 meters long. Okay? And so when you put your values into your trig functions, you can't put a negative value in there because we're comparing ratios of lengths. Questions on this problem?
Do you care if we use inverse tangent versus inverse sine?
Oh no, if you use inverse sine, you're going to have to find that hypotenuse. It'll just take one more step. But there's, as they say, there's more than one way to skin a cat. My daughter has a bachelor's degree in biology. She says that's not true. Just one way. Okay? Okay, it turns out that when we plug into that inverse tangent function, we get about 69 degrees. Okay. Now, we've got 2 minutes. Watch how quick this is. If we look at that banana problem, the banana's in free fall. We set up our list. In this coordinate system, acceleration is minus 10. In this case, you throw the banana at 20 meters per second at 37 degrees. You've all solved this problem, so I can go through it quickly. If I break up the 20 meters per second, I get 16 in the x and 12 in the y. Okay? And the 16 in the x stays 16 in the x. Now again, this is one of those problems where you have these 3 pieces of information that are not independent of each other. So what we do is we set up a wall at x equals 8 meters. And we ask ourselves, if every second it goes 16 meters to the right, how many seconds to go 8 meters to the right? Well, that would be a half a second. And so now, I solve for delta y, given that the time is a half second, and what I get when I solve that is 4.75 meters. If it were 5 meters, it would just barely make it. Again, this was Steve Iger in the original. He didn't get the banana. He started that. Okay, we'll see you tonight at 8 o'clock in this room, and tomorrow we'll have the exam.